This is FE Peer Review, the Flat Earth Peer Review channel. The date is August 31st, 2020. This is a video in response to a problem statement put forward by Ranty regarding the Coriolis effect and objects such as a cannonball which are shot in a ballistic trajectory. So Ranty, I'm looking at this little problem statement you presented, and I prepared a response. The response seems to take about 20 minutes, and it's following this in the video. But I thought I'd start with a very brief summary because I know a lot of people aren't interested in watching the full-length video. In essence, your problem statement has a problem with it. You've defined a launch velocity and a hang time. By hang time, I assume you mean the amount of time it's in the air before it hits the ground. And you can't really define both those things because one is dependent on the other. There's only three factors involved: the velocity, the time, and gravity. And we can't change gravity on Earth anyway, assuming we're doing this on Earth. Can't change gravity. So if we shoot it at a specific speed, then the hang time is determined by the speed we shoot it at. Or conversely, if we want to have a specific hang time, then we have to have that forces us to shoot it at a certain speed. So in the course of solving this little problem, I've ignored the things like air resistance, whether or not this cannonball reaches terminal velocities is coming back down. I've ignored crosswinds. I've ignored that kind of stuff just for the sake of simplifying the problem. But there's no way to achieve a hang time of 1 minute with the ballistic trajectory at the speeds that you gave in your problem statement. So you'll see what's necessary in order to achieve the 1 minute hang time in the course of the solution that follows. One more quick little comment before I dive into the more detailed explanation of the solution. I just wanted to share this interesting resource I found along the way as I was researching these questions. This is the U.S. Army, part of the U.S. Army websites, group of websites, and it's various publications that they have. So it's armypubs.army.mil, and on this page here, I've got a study on the ballistics of a particular type of rifle cartridge. I don't happen to know anything about rifles and cartridges, but I picked it up because it has a reference. It has a little paragraph here. So there's a paragraph here: Coriolis effect results from the motion of the Earth as a bullet is in flight. Typical deflection at 1,000 yards might be 3 inches. They refer to a book for more detailed information. They say that it's basically for the purposes of this particular study and the type of weaponry involved, the distances are such that it doesn't really have an impact. They're talking about a rifle, not a cannon that's shooting an object miles and miles. Anyway, I just thought I'd let you know that that's out there. This is, an American U.S. Army training manual, and it's discussing the influence of Coriolis effect on ballistics. I will do the best I can to make some sense of this. I'm kind of doing it on the fly here. This was the comment you put up. Question for Globers: if you're at the equator and you shoot 2 cannonballs directly north, how much deviance will they encounter due to Coriolis over these parameters? Ball 1, traveling at 275 miles per hour, has a hang time of 1 minute. I'm assuming by hang time you mean the time that it's in the air, from the time you shoot it to the time it hits the ground again, 1 minute. Ball 2, traveling at 550 miles per hour, has a hang time of 1 minute. If you're going to make a comment, please leave it okay, etc. So there are a couple of issues here that we're going to need to sort through. And I wanted to just clarify a couple of points. There's, of course, a lot of on the comments below, you'll see other people have brought this up. I'm gonna make some assumptions that you didn't include in your comment, in your question, such as I'm going to assume it's a nice streamlined object like a perfect sphere, which we're going to assume has no air friction, not realistic but close enough, probably not going to have a big effect on the final results. So we're not going to include air friction, any kind of side side winds blowing it off course, we're going to ignore those. And let's see what else. The mass of the ball, we're just going to assume that it's heavy enough and compact enough that, again, it's not going to raise issues with things like drag, air friction, wind resistance. And finally, we have some problems as far as your hang times. I'm assuming that what you mean by that is the time that it's in the air. From the time that it leaves the cannon to the time it hits the ground again, it's the time in the air. Another assumption I'm going to make is that the surface that it's being shot from is at the same elevation as the surface it's landing on. In other words, we're not shooting it off a mountain into the sea, into a valley or anything like that. The starting point and the ending point are basically at the same elevation. So those are some of our basic assumptions we're starting with. And I wanted to also say I want to outline a couple of points. You're talking about Coriolis. So the implication is that you're shooting it north, and once it leaves the cannon, the Earth is rotating, and the line that you initially sent it on is going to cause it to drift from its intended path as the Earth rotates. I want to mention one other thing here. To make clear, this is what's called sometimes referred to as a ballistic trajectory. Basically, there's no control over the flight path of this object once it leaves the cannon, unlike an airplane. So the stuff we're looking at here has very little, if anything, to do with what happens when an airplane leaves the ground flying from the equator towards the North Pole. That's a completely different problem with a completely different set of issues to consider. And that has been more than adequately addressed many times by other people, including Wolfie6020 and Bob the Science Guy. And I think Blue Marble Science may have done a video on that subject as well. So I'm not going to go there. This has nothing to do with airplanes. This is a ballistic trajectory. So what is a ballistic trajectory? Basically, it's like a cannonball. You shoot a cannonball. You're over here on the far left, and you shoot a cannonball into the air. And once it leaves your cannon at whatever speed, it starts to slow down until at a certain point it flattens out and it starts to accelerate again towards the ground. So there's a deceleration in the vertical. There's a deceleration and then an acceleration. And the angle at which you shoot it is going to control the distance that it travels. That's a ballistic trajectory. So a couple of points here. There's an X component and a Y component to the path that this thing is going to travel. And it depends entirely on the angle, the initial angle. So let's go up here. If you were to shoot your cannonball straight up into the air, effectively, we'll call it straight up. They're showing a slight forward motion, but that's just so that you can see the up versus down path. Your entire, the speed of your cannonball is directly upward. All of the speed is upward, and gravity is pulling back down on it. Whereas when you shoot it at an angle, your speed has two components, a horizontal component and a vertical component. The horizontal component is perpendicular to the force of gravity and is not affected by the force of gravity or resisted by the force of gravity. However, the vertical component is. So the vertical component, which is the upward portion, is causing, gravity is causing that cannonball to decelerate to the point where it's moving, it's reached a zero acceleration at the top. It's not accelerating upward anymore. And then gravity continues to pull on it, and the acceleration is back in the direction of the ground. So that's a ballistic trajectory, and that's the relevance of these angles, because depending on the initial angle, given the same mass at the same initial speed, it's going to travel a different horizontal distance. And when you get to your Coriolis question, I haven't completed the results yet. I'm working on it as I make this video. The horizontal distance it travels may alter our results. So I'm going to assume a 45-degree angle, which gives us the maximum horizontal distance for this problem. So those are the main issues behind this that we have to sort through. And I'm going to pause and work on it some more and come back. So Ranty, we are looking at the next step in the problem statement here. You said you had a hang time of 1 minute. You gave a couple of initial velocities, 275 miles per hour and 550 miles per hour. And there's a fundamental problem with that. And we're going to start by looking at just a very simple vertical trajectory, shooting this cannonball straight up into the air at 275 miles per hour. And we're going to figure out what happens between the moment we shoot it and the moment it hits the ground. So this little chart over here shows the math behind the vertical trajectory. So we are shooting the ball upward, and our distance upward is y. And this equation here gives you its height at any given time t. And the equation is the initial velocity times t minus 1/2 of gravity times t squared. Now what you do is you fill out you complete that equation for a variety of times t, 1 second, 2 seconds, etc. And you get the height at that moment in time. So I've put it all into a spreadsheet here. And for a start, I've converted 275 miles per hour to meters per second, and that's rounding 123. 550 miles per hour rounding gives us 246 meters per second. Gravity is 9.8 meters per second. And then I've made this little table here. We've got the time, a column for time, and a column for height. So at 1 second, at 123 meters per second, 275 miles per hour, at 1 second, our cannonball is 118 feet in the air. At 2 seconds, 226 feet. At 3 seconds, 324.9, and so forth. Now here's where we run into a bit of an issue. We get down to 25 seconds, and moments after 25 seconds is when our cannonball hits the ground. It doesn't, at 26 seconds, it's already into a negative height, which means we've hit the ground. And that is graphed in this arc here. What we're seeing is the height in the vertical axis and the time in the horizontal. So these represent seconds. And at 25 seconds, our cannonball has hit the ground again, which means that at 275 miles per hour initial velocity, we can't have a hang time of 1 minute. It will hit the ground after 25 seconds. So the two things you put in your problem statement are incompatible. So now let's look at 550 miles per hour. That was the other figure you put in there. It's 246 meters per second. And that gives us a hang time of about 50 seconds. So not quite a minute still. And that shows the height relative to the time. And at 50 seconds, it hits the ground. So even the faster of the two will not stay in the air for a minute. So your problem statement is basically it can't be solved because you can't have both things. You can't have an initial velocity of 550 miles per hour and a hang time of 1 minute if we're talking about a cannonball, a ballistic trajectory. One more thing about the vertical trajectory. I just realized it might be useful to figure out how fast we would need to have that cannonball shot in order for it to stay in the air for 1 minute. And I just extended my little table down to cover 60 seconds. And then I fiddled with the launch velocity until I got it so that it was 0 at the end of 60 seconds. The height was 0 at the end of 60 seconds. In other words, up, and then it hits the ground at 60 seconds. And it came up with a launch velocity of 294 meters per second, which is 657.7 miles per hour. Miles per hour. So if you want a 1 minute hang time, you're going to need an initial velocity of 294 meters per second, or 657.7 miles per hour. I just thought I'd add that in because it might be useful in the next step. So here's a little more on ballistic trajectory, and now we're going to look at what happens when you're not shooting it straight up, but rather forward. And it's interesting to go back to this. This is math I haven't looked at in about 35 years. But as I had recalled, and it says it here in this nice little explanation, the launch at 45 degrees gives the maximum range. So that would be the little blue line here. And that was what I was suspecting was the case. So basically what's happening is when you launch it in a forward upward direction, a part of your velocity is traveling on the x path, and that is perpendicular to gravity, so it's not going to slow down. Gravity is not causing it to slow down in its forward direction. It's traveling at a constant speed forward. However, the vertical component of your trajectory is being counteracted by gravity, which is why it finally comes back down to the ground again. So, in fact, it would take exactly the same amount of time for the cannonball to travel along the 60-degree path, the 45-degree path, or the 30-degree path. The amount of time before it hits the ground on any of those three trajectories would be exactly the same. The difference would be how much horizontal distance it covers in the meanwhile, and that's because of different amount of forward versus upward component in the angle at which you're shooting the ball. So once we've solved our initial problem here and determined that we need to shoot it at 294 meters per second or 657 miles per hour in order for it to hang in the air for 1 minute, once we've determined that and we've got our 1 minute, then we know that if we shoot it at a 45-degree angle, we'll get a full minute's worth of forward motion out of that. And then the question is simply, how far does it travel forward in 1 minute? Now, it does not travel forward at 657 miles per hour because part of that motion is forward, part of that motion is upward. But at a 45-degree angle, initial launch at 45-degree angle, I'm going to come back over to my little Excel spreadsheet here. And I've drawn this little square here with this diagonal line. That's a 45-degree angle bisecting that square. I happen to recall just from my head that a unit square, a square with a side measuring 1 unit by 1 unit, the diagonal measures the square root of 2. The square root of 2 is 1.414. It goes on forever. So the horizontal, if that diagonal is our launch velocity, the horizontal component is our launch velocity divided by 1.414. So in the case of our maximum launch velocity to keep us in the air for 1 minute, 294 meters per second, that's right there, we have a forward motion of 207.9 meters per second. And interestingly, that figure does, so that's the figure back up here. That would be at our maximum speed, not at either of the speeds you outlined in your problem, which do not give us a hang time of 1 minute. So I wanted to show something interesting here in this little chart, which is using the same math. You input your launch velocity down here, and that's the 275 miles per hour you gave in your problem statement. And you input your angle here, and that's 45 degrees. And this little chart, using the same math that I used in my Excel spreadsheet, gives you the horizontal velocity at a given time and the vertical velocity at a given time. And what's interesting is that as we change the time, we'll start with 1 second, we see that we have a horizontal velocity of 86.9 and a vertical of 77. As we change the time, the horizontal number never changes. It's the velocity forward remains constant. It's the vertical velocity that changes. It starts out fast, it gets slower until it reaches 0, and then it starts accelerating downwards. So at 1 second, we have 86.9. At 10 seconds, we still have 86.9, but our vertical velocity has dropped. At 20 seconds, still 86.9, but the vertical has dropped. So you see that's a constant forward motion. So where am I going with this? So in order to achieve the hang time of 1 minute and a maximum distance horizontal distance in that minute, we're going to need to up the speed of that cannonball you gave in the problem. So I'm opting to go with the hang time of 1 minute and increase the speed in order to achieve it, rather than use the speeds you gave, which do not give us adequate hang times. So I will now proceed to determine how far forward we travel in 1 minute at that speed there. So coming back to your question, we're at the equator, we're shooting a cannonball due north at such a speed that it will have a hang time of 1 minute, which means faster than you had originally stated in your problem statement above. But I'm going to go with the 1 minute. Since I have to choose between one or the other, I'd rather have a longer hang time, give us a farther flight path. So cannonball is shot due north and is in the air for 1 minute before it hits the ground. So as it's in the air, it's traveling in this northerly direction, and the Earth is rotating. So how much does the Earth rotate in 1 minute is what we need to look at next. So here's my spreadsheet again. And I fixed a little boo-boo that you will, if you're watching close, you will have caught earlier in the video here. The X component, I just want to note the correction. The X component was, I had it written incorrectly up here. I had it correct in the equation. It's the launch velocity divided by the square root of 2, not multiplied by the square root of 2. So our launch velocity we're taking at 294 meters per second, 657 miles per hour. That gives us a hang time of 1 minute. That's our launch velocity. The X component of our launch velocity is that figure divided by the square root of 2, which is right here, by the way. And if you want to see in the Excel spreadsheet, that's the highlighted in red. In miles per hour, that's 465 miles per hour. So the forward component of our launch is 465 miles per hour, which works out to 7 3/4 miles per minute. That's just that divided by 60. In the meanwhile, Earth is rotating in 1 minute, 0.25 degrees. Earth rotates at 15 degrees per hour. 15 per hour. Divide that by 60 and we get 0.25 degrees per minute. The equator has a diameter of 7917.5 miles. So 1/4 of a degree is 5.5 miles. Now, strictly speaking, I'm simplifying just slightly. This is the diameter of the equator, of the Earth at the equator. If we've shot our cannonball 7 3/4 miles, then it's no longer at the equator, and strictly speaking, the diameter of the Earth is slightly smaller, but at that small of a distance, that difference is going to be so tiny that it's not going to really affect our result in a meaningful way. So I've simplified the math. Earth diameter, the 1/4 of a degree of the Earth diameter, it works out to 5.5 miles, which is 29,031 feet. So go up 7 3/4 miles, your ball hits the ground. In the meantime, the Earth has rotated 1/4 of a degree, and the point you were originally aiming at is now 29,000 feet off to the east. So there's your answer. That's, using a number of simplifications. We're ignoring things like wind resistance, whether the ball might reach terminal velocity as it comes back down, things like that. But I just wanted to get at the real essence of what I believe was the essence of the question you were after. And I think the key takeaway is that you really actually asked a kind of an impossible question. You cannot both define the launch velocity and the hang time. So I had to pick between one or the other because one is dependent on the other, and in the figures you gave do not work with the 1 minute hang time. I chose to work with the 1 minute hang time and ignore these velocities. The only other way for this to make these parameters work is to change the acceleration due to gravity. So if you were to create a custom planet that had a different gravitational force acting on the cannonball, then you could adjust your gravity so that at any given speed, you could get a hang time of 1 minute by adjusting gravity. Of course, that's not an option here on Earth, so I didn't follow that route. So there you go. It's kind of a long-winded explanation, but I think it was necessary and worthwhile in order to see the various factors involved in the problem. Hope you found that interesting. I think I'll close it here. Really no more to say. Thanks. Having not thought about or done the math for this kind of a problem for a very, very long time, I'm now just having a few second thoughts on what I put together. And I just want to say if I've missed anything terribly important and critical in terms of the physics or the math involved, and if you catch that and can explain it to me, I would welcome comments on that score. However, if that's the case, it would be really great if you could provide a concrete statement about what's wrong and show me some numbers to help me understand it better. Thanks a lot. Bye. If you enjoyed this little video, please take a moment to like the video and subscribe if you want more. And I believe you can click that bell and there'll be notifications as well. Thanks a lot. Have a great day. Bye-bye.